everyone! Welcome back to integralcalc.com. Today we're going to be talking about how to use the alternating series test to determine whether or not an alternating series converges. And in this particular case we have the sum of the series -1 to the k plus 1 times the square root of k plus 1 minus the square root of k. And we've been asked to determine whether or not this series from k equals 1 to infinity converges or not. So because we have an alternating series, we're going to be using the alternating series test for convergence. And I've taken here a screenshot of the part of the convergence test chart that I have up on my website that talks about the alternating series test. So what we see here is that in order to conclude that an alternating series converges, we have to show two things. One, we need to show that the series a sub n is always greater than the series a sub n plus 1, which is also always greater than 0. And we need to show that the limit as n approaches infinity of the series a sub n is equal to 0. So those are going to be the two things that we need to do, and I'll call them 1 and 2. So we'll start with the first piece, piece number 1, where we need to show that the series a sub n is greater than the series a sub n plus 1, which is greater than 0. Notice here that in our formula, right, for the alternating series, we have here a sub n. We've got a sub n, and then we also have this piece here, which is the alternating series part of the series. What this tells us is that our series is divided into two pieces. The first part, which gives us the alternating series part, and that's going to be the -1 raised to some exponent, whether or not it's k or k minus 1 or k plus 1. That's the alternating series part. Then the second part here, everything after that, is going to be our series a sub n. So this second part right here is going to be a sub n. So we'll use that as a sub n. We need to show that that series a sub n is larger than the series a sub n plus 1. So I'm going to show you two ways to do that. The first is kind of just to get an idea in your head of whether or not it is greater. The second is prove that it's greater. So the first way I'm going to show you is we'll say that the series a sub n is equal to the square root of k plus 1 minus the square root of k. Right? So we have that as the a sub n series. If we start plugging in for k, and we start with 1, right, because they tell us we're starting with 1 here. If we start plugging in, and let's see, we'll get 1, 2, 3, 4, we'll just plug in 4 terms, right? If we plug in 1, we'll get the square root of, we plug it in here and here, right? We'll get the square root of 2 minus the square root of 1. Square root of 2 minus the square root of 1. Then, if we plug in 2, we'll get the square root of 3 minus the square root of 2. Then when we plug in 3, we'll get the square root of 4 minus the square root of 3, and as you can see here, the square root of 5 minus the square root of 4. So those are going to be the terms we're going to get when we plug in 1, 2, 3, and 4 on into infinity, right? We'll get these terms here to repeat. So we'll plug those values in for k. Then if we look at a sub n plus 1, the first thing that we can try is just to replace k with k plus 1. So we'll say k plus 1 is going to go in for k right here. So then we'll have another plus 1. And then we're going to plug in k plus 1 here for the second k. So when we do that, obviously we get the square root of k plus 2 minus the square root of k plus 1. So when we do that, if we plug in again 1, 2, 3, and 4, we'll get, so starting with 1, plugging in 1, we'll get the square root of 3 minus the square root of 2 plus the square root of 4 minus the square root of 3 when we plug in 2 plus the square root of 5 minus the square root of 4, which is what we get when we plug in 3, and then obviously the square root of 6 minus the square root of 5 when we plug in 4. What we can see is that if we compare this first term here, if we compare the square root of 2 minus the square root of 1 to the square root of 3 minus the square root of 2, and then we compare every term in the series, right? When we plug in 2, we got this term, and we got this term. Right? When we compare each one of those terms in the series, what we find is that a sub n, these terms up here, are always greater than the a sub n plus 1 terms. So we conclude that a sub n is greater than a sub n plus 1, what we get when we plug in k plus 1 for k, which is what we want up here, right? We want a sub n to be, you can't see that, we want a sub n to be greater than a sub n plus 1. So that's how we can kind of get an intuitive gut feel that this is going to work. But what we want to do is prove that a sub n is greater than a sub n plus 1. And the way that we can prove it is by taking the derivative of a sub n, the series a sub n. If we take the derivative, it's going to tell us whether or not our series is increasing or decreasing. And if we can show that the series, the derivative is negative, the series is always decreasing, then of course a sub n plus 1, a term further along in the series, will always be less than a sub n, which is what we want to show. So I'll go ahead and show you that now. If you take the derivative of a sub n, we'll say dx of a sub n, the derivative of a sub n, is going to be, and let's go ahead and transform this here into k plus 1 to the 1/2 minus k to the 1/2, which is the same thing as keeping the square roots in there, right? The square root is the same thing as taking what's under the square root and raising it to the 1/2 power. So when we take the derivative, we'll multiply that 1/2 out in front, k plus 1 to the negative 1/2, and then we'll get minus 1/2 times k to the negative 1/2. So when we simplify this, we'll end up with 1 over 2 times the square root of k plus 1, which we get because we move this whole term here, k plus 1 to the negative 1/2. We move that to the denominator to make the 1/2 exponent positive. When we move it from the numerator to the denominator, the exponent becomes positive. And then, of course, we're back at positive 1/2, which is the same thing as the square root. So then, similarly, over here, we've got 1 over 2 times the square root of k. Now, if we want to find a common denominator here, we would just go ahead and multiply this first term times the square root of k over the square root of k, and we'd multiply the second here by the square root of k plus 1 over the square root of k plus 1. When we simplify this, we'll end up with the square root of k minus the square root of k plus 1 all over 2 times the square root of k times the square root of k plus 1. 2 times the square root of k, yep. So now, to simplify further, what we can do is go ahead and multiply by the conjugate. Remember from limits, we can multiply by the conjugate of the numerator here. It's the same two terms, but instead of the negative sign in between them, we put a positive sign. This term right here is the conjugate of the term from our original numerator. So k plus 1, we multiplied the numerator and the denominator by the conjugate so that it's the same thing as multiplying by 1. And when we now multiply these out, we'll get k, right? This times this gives us k. And then we have plus the square root of k times the square root of k plus 1 minus the square root of k times the square root of k plus 1. So that cancels. And then when we multiply these two terms together, we're just left with minus k plus 1. So we get that together, and then in the denominator here, we'll have, and let's combine these two right here. You can combine those by putting everything underneath the square root sign when two square roots are multiplied together. So we'll just do k squared plus k will be underneath the square root sign there. And then we have times the square root of k plus the square root of k plus 1. All right. So now you can see that we've got a k and a minus k. So these two are going to cancel. And all we're left with here, and let me just go ahead and cancel out this whole thing, all we're left with in the numerator is a negative 1. So this is our derivative, right? d dx of a sub n. This is our derivative, And what you can see is that the numerator is always going to be negative, right? It's a -1. The denominator is always going to be positive because our series starts with k equals 1, right? We start with 1. If you plug in 1 or any number larger than 1 in for k into our denominator here, obviously you're going to get +2 there. You're going to get positive underneath the square root sign here, right? Because you'll get a positive number squared plus another positive number is always going to give you a positive number underneath that square root sign. Positive and positive again. So everything in the denominator is positive. So since you've got a negative divided by a positive, that's always going to be a negative, which means that the derivative dx of a sub n is always going to be negative, and so it's always going to be less than 0, which means that the function is always decreasing. So if the function's always decreasing, right, our series basically goes a sub n plus a sub n plus 1 plus a sub n plus 2 plus ... right? Since the series is always decreasing, this will always be a sub n plus 1 will always be less than a sub n plus 2 will always be less than a sub n plus 1, and the series will be constantly decreasing. So we've now proven here that a sub n is greater always than a sub n plus 1. We also know that a sub n plus 1 is always going to be greater than 0, and we can see that over here in our series that we've written out, these terms right here, right? No matter how large you go, right, 400 terms out or whatever, you're going to have the square root of 400 minus the square root of 399. That's always still going to give you a positive number. It will always be positive and therefore always be greater than 0. So we have now officially checked off these two requirements, right? We've proven there that a sub n will always be greater than a sub n plus 1, which will always be greater than 0. So that's how you can prove using the derivative that you've met that first requirement. So now all we need to do is determine whether or not the limit of a sub n as n goes to infinity is equal to 0, number 2. If we can prove that, then we know that this series converges. So let's go ahead and look at that. I'm going to just erase this stuff here so I've got some more room. So to show that the limit is equal to 0, what we'll go ahead and do is take the series a sub n. So remember that the series is the square root of k plus 1 minus the square root of k. Okay, right? This series up here, this is a sub n. And what we want to do is find the limit of this series as n approaches infinity. And we want it to be equal to 0. We can see roughly just by looking at it that it's probably going to be equal to 0. If we plug in infinity for k right here, right, we'll get infinity plus 1, which 1 compared to infinity is nothing. So it's basically infinity. And then we get infinity here. Square root of infinity minus square root of infinity should be 0. But the way that we can prove this is by multiplying again by the conjugate, and that will allow us to see very clearly that the limit is going to be 0 as as k approaches infinity. So we'll multiply by the conjugate, which is square root of k plus 1 plus square root of k. So when we multiply by the conjugate, we'll see that we'll get k plus 1. Then we'll have plus square root of k times square root of k plus 1 minus square root of k times square root of k plus 1, which will cancel each other out. And then we'll just be left with, when we multiply this one by this one, a minus k. So that'll be our numerator. And then in our denominator, we'll end up with square root of k plus 1 plus square root of k. And we want to be finding, of course, the limit as k goes to infinity. So we can see obviously that k and k here are going to cancel. So we'll be left with 1 over the square root of k plus 1 plus the square root of k. And this should make things very clear for us because obviously our denominator now, when we plug in infinity here for k, right? Our whole denominator is going to be very, very, very large, infinitely large, right? And we know from doing lots of these problems that whenever the denominator gets very large, you have 1 over some very large number, or anything really, over some very large number, the answer here is going to be 0, right? Because 1 divided by an extremely large number is always going to tend toward 0. So the limit as k approaches infinity of a sub k, which is our series a sub k or a sub n, is going to be equal to 0. And so now we can say that we have proven the second portion of this requirement. And that now we can say is also met. Both of these requirements we've checked off, and therefore the alternating series test, we've used the alternating series test to prove that this particular series converges. So that's it. I hope this video helped you guys, and I'll see you in the next one.